welcome to another Heidelberg Joint Astronomical Colloquium. After last week's archaeological excursion on the surface of Mars, we welcome today Anna Bonaca of Carnegie Observatories, this time to excavate the halo of the Milky Way. So I invite Anna's host, Didier Crutzen, to introduce Anna.
Thank you very much, Richard. Yeah, it's a real honor to have you here with us this week, Anna. Thank you so much also for coming to Heidelberg in person. It's a real change of pace if we look at the past, what is it now, year and a half. And I'm sure a lot of us will actually be really excited to interact with you this week in person. It's really unique. So to just introduce Anna for a brief bit, Anna is really a world-leading expert on stellar dynamics and galactic archaeology, the disruption of the satellites of the Milky Way, the formation and evolution of tidal streams, and using these to probe the galactic halo structure and substructure and eventually the nature of dark matter. So Anna started her sort of graduate career at Yale, where she received her PhD in 2016 after working with Mala Jiha there. She received the Brouwer Prize of Yale University for her PhD thesis. And then until this year, until this summer, she was I2C fellow at the Institute for Theory and Computation at Harvard. And since September now, she is a staff scientist at Carnegie Observatories. So Anna, I'm really looking forward to your talk. Before your talk, I should already mention that because we are now in this unique opportunity to do this, we're actually having a colloquium dinner tonight. So think about that already during the talk. And we'll discuss coordinates after the talk is finished. But Anna, for now, please, if you would like to go ahead, and the floor is all yours. I look forward to it.
Thank you. Thank you so much for having me here and inviting me for an in-person option as well. It is really great to be here, and already I've seen some people and hope to see many more of you throughout the week. So the past few years have been really exciting in my field of research, studying the Milky Way, and it really has mostly been thanks to the Gaia mission, which transformed our view of the galaxy from this static image, which is also very beautiful, but we just now have so much more information because Gaia provides us with proper motions and in some cases radial velocities and parallaxes of almost 2 billion stars. So instead of just having this image of the Milky Way, we can play the movie and see how the stars are moving, where they come from, and how this whole galaxy formed. And the way I like to think about the Milky Way is sort of as a cosmological laboratory, because in these motions of stars and their chemical properties and ages, we have encoded 13 billion years of cosmological evolution. And so digging into this data set allows us to ask some deep questions about the very nature of the universe. And on the very, really biggest scale, those questions that I'll be trying to address is, what is the universe made of, and where do we come from? And so these questions are very broad, and in some sense, probably all of us are answering some aspect of it. So to be a little bit more specific in terms of where do we come from, I'll be talking about how the Milky Way formed. And when we look at the galaxies, other galaxies throughout the cosmic history, such as those shown here in the Hubble Ultra Deep Field, we see that a variety of physical processes are at play, and merging of smaller galaxies to become part of a bigger whole, like our Milky Way today, is one important process. And of course, in other galaxies, we can see that in different stages for different galaxies. But in Milky Way, we actually have the opportunity to unravel this process, to identify the individual progenitor galaxies of the Milky Way and see when and how they merged into our own galaxy. And in such way, learn something more general about the formation of galaxies overall, not just our own galaxy. So this will be a specific goal for this part of the talk, to reconstruct the Milky Way's formation history. And before Gaia, most of our knowledge of galaxy formation was coming from information about chemistry, chemical abundances of stars. And so here on the left-hand side, I'm showing the familiar plane where on the y-axis we have the ratio of the alpha element abundances over iron, and on the x-axis we have iron over hydrogen abundance. And those are all scaled to solar metallicity. So the sun marked with a circle with a dot is at 0, 0. And the stars here is a sample from the apogee survey from SDSS. And you can see that most of the stars in the Milky Way that apogee survey are in this cloud at kind of low alpha element abundances and high metallicity, where sun is. And a couple of years ago, we were fortunate enough that Gaia provided us the first proper motions for something like 6 million stars, and there are some overlap with apogee. So what we were able to do is then take stars from the same cloud where the sun is and check what their orbits look like. And what we found, unsurprisingly, is that most of these stars are on disk-like orbits, so orbiting in a disk, much like our sun. So if we then move to the second island in this chemical space, the one up above that has also fairly high abundance of iron, but also a slightly higher abundance of alpha elements, we see that those stars also have fairly disk-like orbits, but sometimes they kind of get farther above the plane. And this is this distinction was previously known also as the thin disk, which would be the yellow stars, and the thick disk, these red stars. And those stars were thought to have formed in the Milky Way in the gas disk, and then their orbits are now continuing in this disk. And as a final group of stars that we'll look at, or final metallicity group rather, we have the stars at lower metallicities, which are presumably accreted from lower mass dwarf galaxies that never managed to enrich their stellar population much, so they remained metal-poor and came to the Milky Way on a variety of orbits. And so when we look at their orbits today, they're also more kind of spherically mixed and hotter orbits that populate the so-called stellar halo. So this is kind of our depiction of how, in principle, galaxies form. But with this new Gaia data set, we found a curious new population. And those are the stars that kind of were still part of this disk-like high metallicity, high alpha abundance population, but whose orbits were more like halo, that were kind of moving farther away from the disk than we would naively expect. And we were quite puzzled when we found this population and wanted to understand where it came from. And to do that, we really had to combine both the chemical information and the orbital information. And we're fortunate enough that this improvement in the kind of observational data that we're getting has been matched by the progress on the side of numerical simulations that have been able to produce galaxies much like we observe today. And so I went to ask some of my collaborators who have worked on the FIRE suite of simulations, and I asked them for access to their Milky Way-like high-resolution zoom-in cosmological simulation. And there I selected, the same way we selected observed stars in Gaia, I selected stars that are on halo-like orbits in the simulation, or rather star particles. And because this is a simulation, I could actually ask when those stars form and where they formed. And this is what is shown in this figure over here. So we have on the y-axis the formation distance from the host galaxy, so from the center of that Milky Way galaxy, and on the x-axis we have age, and the color coding is by metallicity. So there are several things to note. First is that indeed there are some of this population of metal-rich stars, so metallicity is higher than minus 0.5 dex, that end up in the stellar halo of a solar neighborhood-like environment in this simulation. So this is already encouraging that such a population that we found in the data has also been independently produced in the simulation. And then the second thing to note is that there is a wide range of distances where these star particles formed. So on the y-axis, we see that it goes away from basically the center of the galaxy to hundreds of kiloparsecs away. So really, there are kind of two regimes in which stars have formed that have become part of the stellar halo of the in the simulation, and hopefully also the Milky Way as well. So you see stars that were formed in dwarf galaxies and then accreted as when those dwarf galaxies fell into the potential well of the Milky Way. And these are mainly more metal poor stars. On the bottom side here, we see that those that are preferentially metal rich formed in the inner parts of the galaxies and were of the galaxy, and then were subsequently kicked out on more halo-like orbits that we observe today. So we have the dual accrete from the dwarf galaxies and formed in situ and kicked out of that primordial disk, origin of the stellar halo of the Milky Way. And this has been exciting because it shows that we really, by this kind of work where we combine the chemistry and orbital information, we can learn about how our galaxy formed. And so we wanted to go one step further and continue along this way. And a crucial part of this endeavor was having spectroscopic complement to the Gaia data. And so to push this idea forward, at Harvard, we launched the spectroscopic survey of the halo called H3, which there are like many H's that stand for hectoshell in the halo at high resolution. So this is a spectroscopic survey that selects stars blindly. So we only select stars that have small parallax, such that we are excluding most of the disk stars and presumably getting high resolution of our 30,000 spectra between 16 and 18 magnitude to really complement like the final Gaia release that will go to the 16 magnitude. And so the survey has been going on for 4 years now, and the progress is shown here in the figure. We are targeting, or at least the initial idea was to target the high latitude field to further ensure that we are mostly getting halo stars. But as you can see here on the southern galactic hemisphere, we actually have completed all of our initial footprint. So we started going to the lower latitude fields as well. And we've had some exciting initial findings about the stellar halo being more metal rich than we thought previously. We estimated or put the lower limit on the total mass of the Milky Way, and more recently measured the wide binary fraction both in disk and the halo, and found they're pretty similar there. And but what I wanted to talk about now is really asking this question of how do we identify progenitor galaxies of the Milky Way? And now with this data set in hand, we are able to conduct sort of an experiment that was proposed by Amina Helmi more than 20 years ago. And I will show what it means here. So what Amina noticed is that when dwarf galaxies, the progenitors of the Milky Way, are merging in, they are losing stars because they're being pulled apart by the tidal forces. And in the space, like the spatial coordinates, you can see that like we form these long tidal tails, and that with time they kind of continue to mix. And if we didn't really have all of the points here marked by color, it would be hard to tell apart which star after billions of years was part of which dwarf galaxy. But this is just in the spatial coordinates if we only had positions of these stars. However, if we look at the phase space, which is shown here on the right-hand side, we see that in the space of energy and angular momentum, the positions of these stars are conserved. And so if we have these measurements, which can be calculated if we have the 6D position, so the 3D position of the star and the 3D velocity vector, we can actually place stars in this figure. And just a second. Sorry about that. So what we can now do is really identify individual progenitors of the Milky Way from their clumping in this phase space of energy and angular momentum. And now I will show some work from the Harvard graduate student, Rohan Naidu, who really did just that. So this is now H3 data showing the giant stars observed in the by mid 2020, showing them on the left-hand side in the spatial their spatial position. So with this edge on, the position of the sun marked with the star, and then on the right-hand side in the phase space. And so, as you can see, the phase space, there's a lot of structure. It's not uniform. There's like this thick over the density at low angular momentum or radial orbits, and then another one here. And Rohan did a very careful job of analyzing all of these structures, and both in the phase space and complementing it with some chemistry and other conserved quantities of orbital properties. And what he ended up is with this census of different origins of all of the stars in the stellar halo. So here, some of the previously known progenitors like the gas oxygen Enceladus is shown in light green, and then in this magenta or purple, there's the Sagittarius dwarf galaxy. This high alpha population that is part of the thick disk and part of the in situ halo is shown here in pink. But then what Rohan did is when he kind of subtracted all of these previously known structures, is there a number of smaller progenitors like the Itoi or the Wukong over here. And as a result, Rohan was able to really assign the origin to 95% of the stars in this sample. So this is really exciting, but because it really seems that we can identify all of the progenitors of the Milky Way. However, like the lower mass one will be less well sampled, so we'll need more data. So I'll just like update with the data we had just collected until this last few weeks. So this is what Rohan had initially, and this is what the diagram looks like now. So you can already see that there's like some clumpiness, like over here, the clumps that appear in the new data set that were absent before. So there's clearly more work to be done to really get to the lowest mass and presumably more numerous progenitors of the galaxy by analyzing the future data. But this is, as I mentioned, just the giant stars. There are, of course, a number of other stars that are part of our catalog. And I wanted to specifically mention the main sequence turn-off stars because they provide us very good information about the ages of these stars. So this is shown in here on the left-hand side is the so-called Keel diagram, which shows the log G or the surface gravity of the star versus its effective temperature on the x-axis. And the color coding is by the fractional age uncertainty. So you can see that in this region around the main sequence turnoff, we get a very precise measurement of ages. So I selected here just stars in this certain range of surface gravity, where the median age uncertainty is only 10%. And so, of course, our sample, because we're looking at less luminous stars, is now more spatially constrained than what the Rohan used in his sample. But this really allows us to at least get the age distribution of different major components of the galaxy. And here the two big ones, the two big halo components. Like, so I'm making a selection only in chemistry, with the accreted halo being more metal poor and the in situ halo being more metal rich. And the disk components are now shown as dotted lines. So the high alpha disk has the same chemical abundances, the in-situ halo just on disk-like orbits, and the low alpha disk has a lower alpha element abundances. As you can see that there is a clear difference between the age distribution of the accreted halo and the in-situ halo. And we think this points to a picture where most of this distribution of stars has really been shaped by a single major merger around 10 billion years ago. So before the merger, most stars forming into the Milky Way were in this kind of thickless, like high alpha abundances, whereas a smaller dwarf galaxy was forming stars at lower metallicity. However, once this dwarf galaxy fell into the gravitational potential of the Milky Way, it deposited its stars, shown here now as blue squares, to the stellar halo, and then also kicked out some of the existing stars that were born in the Milky Way disk, primordial disk, onto these halo-like orbits, which are now these reddish squares. And finally, since this was happening at such a high redshift, so most, basically redshift of 2, we expect the dwarf galaxy to have been fairly rich in gas, which got deposited into the disk of the Milky Way and then changed its metallicity to start growing this low alpha component. And so to wrap up this part of the story of what we've learned about the formation of the Milky Way, we can now really confidently say that we have identified the most massive galaxies accreted onto our galaxy, and have also been able to quantify the impact of these early mergers. And taking this, maybe now we're taking most of it for granted, but this picture really confirms the cosmological paradigm in which galaxies form hierarchically. And underpinning this idea is that every galaxy is surrounded by a halo of dark matter. And in the fiducial model, or the standard cosmological model, the dark matter is a cold particle, which is massive and weakly interacting. And because this particle is so massive, it can clump on very small scales. So here I'm showing a snapshot of the Aquarius simulated dark matter halo around the Milky Way sized of a Milky Way sized host. And you can see that the distribution is very clumpy. There's a number of these smaller, so the so-called subhalos populating this larger halo. And the big question is, of course, whether this is what halos or dark matter halos actually look like. Most of the mass is in this component, which we don't know what it is. So this question of what the universe is made of, like the second question I posed at the very beginning, at least the way I will be addressing it will be on what is the nature of dark matter. And more specifically, it will be to measure the small scale structure of dark matter halo of the Milky Way. And of course, like what we want to learn is whether the halo is as grainy as predicted in the standard cosmological picture. However, simulators like ANALISA have shown us that none of these small halos are able to form stars, so they should be completely dark and fairly low mass, so kind of hard to detect gravitationally. But fortunately, nature has provided us with a set of sensitive gravitational antennae that can help us in this regard. And they come in the form of tidally dissolved globular clusters. So when a globular cluster orbits the Milky Way galaxy, and here is again shown to scale with the disk and the position of the sun, some stars occasionally gain enough energy to leave the cluster and become unbound. But because they are barely leaving the cluster, their orbits pretty much remains similar to that of the cluster. So the resulting tidal stream is very cold, kinematically cold, and thin and narrow. And as you can see in this simulation, it is like globular clusters are orbiting in a big volume of the galaxy. So the idea is that maybe if such objects encountered something along the way, like a gravitational perturbation, it would somehow be recorded in the distribution of stars in the stellar stream. And to test this idea, I created here a numerical experiment where I'm showing a stream simulated in a smooth galaxy, and its structure, or which cosmologically might correspond to a dark matter, a warm dark matter model that doesn't have a lot of substructure, like this figure shown in the left. And the stellar stream, you can see that it has maybe some structure here, but by and large, it's a one-dimensional, really a string in space. However, when I simulated this a globular cluster on the same orbit in a live dark matter halo in the Via Lactea simulation that has its cosmological suite of subhalos that were interacting with star particles in the stream, I got, as a result, a stream that looks much more perturbed than what we have on top. So there are these regions where there are parts of the streams that are that have higher density, lower density. Some stars are kind of kicked out of the stream. And here, like on the left, we have part of the stream that looks like it was detached from the rest of it. And so, in a sense, this is what we want to ask of stellar streams in the Milky Way. Do they look more like the one on top, which would mean that there's little structure in the dark matter halo of our galaxy, or are they as perturbed as what we expect in a cold dark matter case? So to do that, we of course need to first find streams. And a big breakthrough came with large photometric surveys of the sky. So here I'm showing a view of the stellar halo of the Milky Way I made using data from the Sloan Digital Sky Survey. And this every pixel in this image is showing a weighted density of stars likely to be old and metal poor, and the different colors are mapped to different distances. And then as a first thing, you notice there is a lot of structure in this place. So the bright spots are the still bound dwarf galaxies and globular clusters, whereas the more diffuse structures are what we were hoping to find. So these are the stellar streams, the dissolved satellites of the Milky Way. The most massive one is the Sagittarius stream. So these are the tidal tails of the Sagittarius dwarf galaxy. And the kind of streams that I'm most interested in are the ones from dissolving globular clusters, such as these tidal tails around Palomar 5, shown here on the bottom left. So you can see that these are much, or this Palomar 5 is much thinner than the Sagittarius. And an object of particular interest is also shown here, as is this so-called GD1 stellar stream that starts here at the bottom right, and then arcs up to the top left. And in this case, we haven't found a progenitor, so we think, but because the stream is so thin, we think this is a completely dissolved globular cluster. And because it is so long, we thought it was a perfect candidate to look for signatures of perturbation. And looking at this figure, might think that some parts are a little bit brighter than some other parts, but then we also see this amount of variation just in this other parts of the map where we don't have the stream. So it was hard, just based on this data, it was hard to say whether these variations are intrinsic to the stream or just a part of the contamination of other stars in the Milky Way halo. However, this all changed with the second release of the Gaia data, and it was a very exciting time. I teamed up with Adrian Price-Whelan, who is now a member at the Flatiron Institute at the Center for Computational Astrophysics. And we were part of this kind of unboxing the Gaia data, the 0-day event at Flatiron Institute on April 25th of 2018. And what we decided to do was look into what the GD1 stream, how GD1 stream looks like in the Gaia data. So since we knew where the stream was on the sky, or where it is supposed to be, we knew which part of the Gaia cataloged the query. So I'll just walk you here through through our steps. And so I'll be showing the Gaia stars in and their spatial sky positions in this phi1, phi2 coordinates. And this is just a reference frame rotated such that the stream would appear at the phi2 coordinate of 0. And so the first selection here shows just Gaia stars which have parallax smaller than 1 millirad second. So with that, you see that, okay, there's still a lot of other stars and the stream really hasn't popped up yet. But then if we add just one more selection criteria, and this is that the proper motions of these stars are along this stream, so so that they have very small proper motion in the phi2 direction, and that they're retrograde, so moving basically in the opposite direction from everything else into the galaxy, we already see the stream show up. And this is really amazing because with these two queries, we could do a better job of identifying members of the GD1 stream than what I did when I was a PhD student in a whole semester of work. However, like we still only use the kinematic data here. And now to add the photometric data that I'd used previously, we can then select stars that are old and metal poor at this part of likely main sequence at this distance of 8 kiloparsecs. And this now really reduces contamination of the Milky Way stars a lot. And this is very exciting and all really came on the day of the data release. When we were for the first time able to see that like this stellar stream actually does have significant variations in density. There looks like there's a significant gap at -20 degrees, another one at -4 degrees. But what we were surprised about is that it looked like there are some parts, like some slight overdensities of stream stars that are beyond the stream, like over here, this sort of spur off of the stream or above the stream, and then slightly more diffuse overdensity below the stream. And these are fairly slight. It looks like very low number statistics. However, if we calculate the likelihood that these are part of a smooth background or part of an additional component, it turns out they have a probability of larger than 50% to be part of an additional component and not of the uniform background that is kind of projected along the stream in all other fields. So this now really, like this test that we wanted to do, yielded a result that it turns out that there is a dynamical perturbation of at least this stellar stream in the Milky Way galaxy. And so after Adrian and I quickly wrote this up to share the excitement, I then spent basically 6 months developing numerical models to try and reproduce this structure. And so in particular, we were focusing on this part that has the gap and the spur of stars, which seemed like it would be a fairly unique morphology. And what we ended up with is this model of the GD1 stellar stream that something like 500 million years ago encountered a massive compact object that gave velocity kick to the nearby stars, that changed their orbits. So they're now opened up the gap in the stream, and those orbits are now on this loop precessing around the original orbit of the stream. And when we kind of zoom in into it today, we see both this underdensity and this projected spur of stars off of the stream. And when we look at this model in the space of observable data, we see that actually the position and the size of the gap match fairly well what we observe in the data. So the observed stream is on the top and the model is on the bottom. So we see that the gap position looks pretty similar, as well as the extent of the spur object. And the properties of the impact are shown here on the left. And most excitingly, the mass of this perturber is 5 million solar masses. If shown that this was a dark matter subhalo, this would put a very strong constraint on the mass of the warm dark matter particle, which is a factor of more than 2 stronger than our current limits. But of course, this is just one possible model that kind of shows that it is possible to get such a morphology out of an impact to the stream. However, we also want to understand sort of how well all of these parameters are constrained. So I will present here just results on the constraints on the mass and the size of the perturber that match the global morphology, like the positions of this gap and the spur source in this GD1 stream. And so you can see, so the constraints of this mass on the y-axis and size on the x-axis plane are shown as a gray shaded region. And some of the known objects of the Milky Way, compact objects of the Milky Way, are shown as points. So we have globular clusters as triangles, dwarf galaxies as squares, and giant molecular clouds as circles. And to kind of orient ourselves, dark matter subhalos would live in this teal band, and the dotted lines are showing the 1, 2, and 3 sigma scattered around the mean relation, the mass concentration relation. And so looking at this at face value, it really looks like that the GD1 perturber is preferring compact compact objects, something more like a globular cluster than a dark matter subhalo. However, when we looked at the orbits of known globular clusters in the Milky Way, we couldn't really find solutions of them of any of these globular clusters coming close enough to the GD1 stream to produce this disturbance that we observe. And so, and the similar goes for the dwarf galaxies and the orbits of molecular clouds. So if we exclude all of these objects, then suddenly we have a very empty looking plot and a kind of continued mystery in our hands, because something happened to the stream, but it's still a question of what exactly. And so it might have been an unseen globular cluster hiding, say, behind a disk. It might have been an unusually dense dark matter subhalo. Our solution is also completely consistent with it being a supermassive black hole. GD1 is a stream in the halo, so I guess astrophysically it would be a little bit hard to see immediately what would a supermassive black hole be doing on such a unusual orbit. But in principle, yeah, we a very compact point mass object like a black hole could produce this impact. So the search is still afoot, but I think the most interesting part is that we have observed such a signature of a perturbed stellar stream, and so we now have a way to search for the subhalos, and possibly this already has been a signature of a dark matter subhalo interacting with a stellar stream. So there are like different ways to kind of continue the talk, and I'm happy to talk more about how we are following up on the GD1 object to see if it actually was a dark matter subhalo. But I wanted to take a little bit broader picture in this last few minutes. And so one of the directions that I am very excited to go to is see what other streams are doing. So as this picture shows, we are, like the cosmological model predicts a huge population of these dark matter subhalos. And this means that impacts such as this one that we saw on the GD1 stream should be fairly common. And so I'll now just show 3 cases of different stellar streams that we have looked in a bit more detail than was after their immediate discovery. And in each case, we found something unusual. So the first one here is the JLM stellar stream that is shown here as an overdensity of stars. It's pretty clear, but what is unusual is that there appears to be 2 components to the stream, one that is thin and another a wider envelope around it. Then in the case of the Palomar 5 tidal tails, now we went back to this system with a dark energy camera and obtained much deeper observations than what you saw in that first figure. And here again, we found evidence of density variations along the stream. So we have dense part and underdense, like a gap over here in the trailing tail, another gap in the leading tail, and even a large widening or fanning out of the leading tail. So again, the possible signature of some sort of dynamical perturbation. And finally, the case of the Alika-Uma and the Atlas streams, which were originally thought at discovery just based on photometric data to be individual, like distinct stellar streams, but after Tingley obtained as radial velocities for both streams, found that like their radial velocity gradient is consistent across these 2 streams, and it really looks like they're part of the same system that got disrupted, much like what we saw in the simulated stream at the earlier part of the talk. And so it's basically the statement holds that every stream that we have looked at in more detail has shown some sort of dynamical perturbation. And then the question is, what happened to it? So was and in the case of JLM, there's a question of whether this was something formed into the Milky Way or inherited from its own progenitor. In the case of Palomar 5, I work here with Sarah Pearson and Jeremy Price-Whelan. We showed that some of these structures can actually be introduced by interactions between the stellar stream and the galactic bar, or rotating galactic bar. And then in the case of Alika-Uma and Atlas streams, Ting and collaborators showed that a close passage of the Sagittarius dwarf galaxy can show perturbation like seen here. And so really to understand what is happening to the stellar streams, we need to understand what the galaxy or like the whole environment is doing. And the importance of this, I will demonstrate here by a simulation of Nico Garavita-Camargo, who simulated an interaction of the Large Magellanic Cloud in falling into the Milky Way galaxy. And so what is shown here is the distribution of dark matter particles. You can see that this distribution is very anisotropic. So there is just a lot of structure, especially in the outer galaxy. And what we found now looking at, and anyway, it's been shown in many different ways. I'll show like exactly what the stellar halo is doing in this regime by showing the density map of K-giants between the 60 kiloparsecs and 100 kiloparsecs selected using Gaia and WISE photometry. And what we found is that this outer halo, stellar halo, is also anisotropic in exactly the same way as what we would expect from Nico's simulation, so that we have this local wake of the caused by the passage of the LMC, as well as this, on the other hand, kind of axis of halo stars as a kind of global response of the stellar halo and dark matter halo as well to the passage of these massive galaxies. And so this is all happening like with the LMC, but even with all of the other mergers that we identified previously. So really to understand what is kind of happening to the stellar streams at the microscopic scale, and to map out what or to kind of be convinced to robustly state whether some signature is part of the inherited due to the larger environment, interactions with the host or other dwarf galaxies, or really a signature of dark matter subhalo interactions, we need to know more about the origins of stellar streams. So I will go back to this plane of energy and angular momentum, because this turned out to be a useful plane to find the origin of the Milky Way stars, and show where streams lie over here. As you can see already, that there are some parts that are kind of overdense in stars, have a lot more streams. And this is not just by eye. If we kind of scale both the energy and the angular momentum by their dispersion, such as we have a better metric of space, we can calculate the correlation function between the stream positions and the stream and star positions, and see that there really are that the streams are correlated on two specific scales. The small scale sort of corresponds to these individual islands of stellar streams, and the large scale corresponds to the distance between these different groups of streams. I think this shows that most of the stellar streams that are orbiting the Milky Way actually have been accreted as part of a progenitor dwarf galaxy. And so this is why they remain kind of coherent as parts of these islands in the phase space. And this already gives like a huge leg up in understanding of what kind of journey they might have had coming into the Milky Way. For example, Atlas and Alikauma are part of this group here. So maybe then we can expect at least some of the structure to not be due to interactions with dark matter subhalos in the Milky Way, but some other interactions with their host galaxy as well. And this is, I think, shows the promise of looking at stellar streams as a population. And part of my stay here for the whole week is to continue working on this large sample of stellar streams that I'm analyzing with Dietrich, where we are looking at the sample of more than 20 stellar streams and now refining their orbits. And as we are kind of cycling through the different stellar streams and highlighting their orbits as we zoom out from the center of the galaxy, you can see that this is a nice way to get a comprehensive view of the galaxy overall. Like the different streams are now parts like being observed in different parts of the galaxy, and also where orbit in the past they had different orbits. So each of them is providing us some unique information, and as a whole, we can, I think, hope to disentangle all of these intertwined processes of both galaxy formation and dark matter physics. So I'll stop here and take any questions you might have. Thanks.
Just thanking Anna, and I think it's going to be a really big deal if you get into the dark matter through these techniques. I'm sure there's lots of questions, so we have time for maybe 5 or 6 minutes of questions. Please write in the chat if you can't do it acoustically. Walter Dalen.
I wasn't expecting to be first. I only have a technical question. You know, surely the assumed gravitational model for the Milky Way makes a difference here for these orbits and where you put the energy, and also the errors that you have for the stars, for the astrometry and for the distance make a difference where you put them in this angular momentum energy diagram. How important are these details?
Right, that's a great question. So I think the largest source of uncertainty here is the distance uncertainty. And in some way, spectroscopy also helps us there, because we can get an estimate of the luminosity of the star. So we get a better knowledge of distance than just what would be possible with parallax. Yeah, but definitely it isn't like a large source of uncertainty here. And I'd say for the, or maybe I should go to this this previous slide. So for the different progenitors that have been identified so far, like all of them have been also vetted in chemistry. So say all of these are real structures. But I think the real question is kind of going further to lower mass objects where we have fewer stars, kind of how likely those, how confident we can be in the kind of next set of objects to discover. And in that sense, I'm kind of optimistic about this combined efforts between the stars and the streams. So for example, looking just in stars like this, I wouldn't really be very certain of calling this an overdensity, because just for this reason, I think distance uncertainties are larger than that. But the fact that there appear to be two stellar streams, this similar part of the phase space, I think kind of brings, further evidence that this actually might be physical.
Okay, thank you. I guess move on to the next question by Ben Keller.
Hi, yeah, amazing talk. The stream that you looked at, GD1, really eye-popping results. I was curious, seeing that plot that constrains the mass and size of the perturber, and I mean, it seems to me that this, especially when you talk about ruling out the globulars and dwarfs from the fact that we know their orbits, seems like supermassive black holes are an obvious candidate for this. I was wondering, I know there's a fairly recent prediction from Michael Tremmel using the Romulus simulations that most Milky Way mass halos should have a dozen or so wandering supermassive black holes in their halos. Have you looked at, I don't know if there's anyone else who's done this in simulations, whether or not the sort of orbital parameters you get for these wandering supermassive black holes adds or subtracts confidence to the idea that this could be a black hole that's causing this gap in the stream?
Yeah, that's a really great question. And maybe like a year ago, I would have thought that this would be very unlikely, that this was, even like taking into account like Michael's prediction that there should be like a dozen black holes orbiting around, because I was just thinking geometrically, and it would seem that it was very unlikely for one of those dozen to actually impact. Like the stream is very thin. This needs to be come very close to actually make an impact, like within 100 or 50 parsecs, basically. However, I think what's again, going back to here and this picture, where we now seems that all of these globular cluster stream progenitors came with a dwarf galaxy. So I think that changes the picture, because presumably every one of these dwarf galaxies that merged had its own supermassive black hole, or I don't know if it's super where the limit is, but it had its black hole. And if my initial intuition was that the orbits of the stream would be uncorrelated with the orbit of these, or orbits of these black holes. But I think now we have evidence that this, or good reason to believe this would not be the case. So I think now it actually is worth revisiting this question. And I will just make a plug to the answer to Walter's question that I didn't get around to. In that case, the actual gravitational potential we assume for modeling this interaction becomes very important, because we really are interested in kind of parsec scales, kind of distances. And so I think this is a lot of work to be done, but I think it's looking promising, and it would be really fun to to find a halo supermassive black hole this way.
Okay, Kayati Malhan, please.
Hey Anna, it's
Oh, hi, Kathy.
really nice talk and wonderful work. Of course, I had just two quick questions. In fact, they're follow-up of the previous questions at some level. In regard to this GD1 perturbation, I mean, your solutions appear more consistent with the globular cluster population and the black hole population. So what are the chances of these two scenarios where the perturbation was in fact by a globular cluster? Perhaps that globular cluster has been completely disrupted by now, and we should have detected in the form of stream, for instance. And the second question is that, I mean, we know that at some level that there could be a population of black holes inside globular clusters. So maybe it was a globular cluster which had a black hole and then it perturbed, for instance. I mean, I know these are quite complicated scenarios to explore, but what's your personal take on it?
Yeah, that's I mean, as I said, like I think a similar kind of shift in my intuition that goes for black holes goes also for globular clusters. And in fact, I am now revisiting like with the updated Gaia parameters on globular clusters, I am now revisiting like this question of whether maybe there is a solution for at least some of one of the globular, like known globular clusters to have hit the stream. And so I don't have a numerical answer for you of kind of how likely that is. I think, yeah, that would be I think a great question to answer from in the context of cosmological simulations, because yeah, based on what I said, I think those should not be negligible. At least I think that could be a source of perturbation. Yeah, I think. Yeah, you can talk more about it. I think there are like some solutions, like for some globular clusters that maybe, you know, one of them kind of can come close, and now I'm following up on that to see whether the exact morphology of the gap and the spur can be created in that case. For example, yeah, so for some obviously are not, you know, so, because orbits are, or at least orbital orientations are fixed. So even in the case where I can kind of find a region of parameter space where the globular cluster does come close to the stream, like the spur is created on like the opposite side, so that can be ruled out. But yeah.
I have one very quick question, if Richard would allow.
Very quick, we got two more on the pipeline.
Okay, sure. Thank you, Anna.
Sure.
Yeah. Okay, just two more questions. Firstly, Ralph, please.
Yes, also from my side, I think this is extremely impressive, and it changes at least my view of the Milky Way and it being a, you know, unperturbed system, which is certainly not the case. So I'm wondering, you looked mostly at stars from Gaia and other stellar surveys. What is there to be gained from looking at gas? Does someone do that? Are there surveys out there? I mean, there is hot ionized gas in the Milky Way halo. There are high velocity clouds. There is also lots of structure out there in the gaseous component. And so I was wondering whether you have looked at any possible connections with the science questions you have been addressing to the gas observations.
Yeah, that's a good question. I really have been personally more focusing on the stars myself, but of course there's this giant Magellanic stream, which is been known in gas for a long time, and the stellar counterpart has been searched for a long time, and really coming out shorter until very recently. And in fact, yeah, I don't have a slide here, but we did find some of the stars, kind of very few, but kind of outlining outlining the Magellanic stream. Like in gas, we found like some stars that appear to be at the same distance and moving kind of in the same way as a counterpart to that. And so like for I would imagine in the context of these older merger events that probably there's not much information in gas left, but for the Magellanic Stream, there should be. And in fact, people have found a young open cluster that looks to be associated with the stream. And I think the leading hypothesis is now that it, like as it kind of went through the Milky Way disk, it shocked gas and created this small very young open cluster that is, and then continued along its way. So it's now like high above the disk. So I think there is, yeah, it's an interesting question to follow up on what, and I would say that this really the case of Large Magellanic Cloud kind of merging in would be the most relevant one, where we can really learn more about this, what happens when gas kind of gets into the galaxy. And I don't know, yeah, to be honest, I don't really know much about the hot halo and what can be learned there, but I'd be happy to talk more and learn.
Okay, cool, thanks.
Thank you.
Okay, one last question. That's from Diederik. Go ahead.
Yeah, really wonderful talk, Anna. Of course, really brilliant work. First, am I audible? Because I understood that before I was a little bit quiet, so I increased the volume of the microphone.
Fine.
Okay, good. So yeah, my question is about the assembly history of the Milky Way that the first part of the talk was about. Of course, you omitted the most major merger that the Milky Way experienced, Kraken, and there was a good reason for that, and that is that that H3 basically targets outside the solar circle pretty much. Now, a lot of the early assembly of the Milky Way probably took place with debris that we now see within the solar circle, that would now be situated within the solar circle. What do you think are the prospects of starting to disentangle sort of the inner part of the halo, right? The median galactocentric radius of globular clusters is 5 kiloparsecs only. There must be a lot going on there, and a lot of it is probably phase mixed, but what do you think are the opportunities there?
This is part of the galaxy that I haven't really thought about a lot. But just, I mean, I guess the obvious question, and maybe this is, as for the benefit of people deciding about the infrared Gaia, that would be great. I would imagine, yeah, that really, well, I mean, we are demonstrating, yeah, how much you can do with when you have the full phase space. So yeah, having a similar amount of data in the inner galaxy, I think would be yeah, open up many windows that yeah, we currently don't have into that area. And as for how long kind of the dynamical signatures are preserved, I don't know. I would imagine that we can push further in that we have pushed now, maybe like in the very inner region, it might be very phase mixed. But for example, this stream over here is the so-called Ophiuchus stream that is very close to the bulge, and it is an unusual object. So it looks like, anyway, the stream is fairly short, so much shorter than one would imagine it being for its stellar age. So I think even in that case where kind of dynamical signatures are being kind of erased fast, it looks like there are still new things coming in that can give us some estimate of what is dynamically happening now, and kind of be helpful in understanding dynamics of that volume of the galaxy. So yeah, I would say like large survey on proper motions in the inner galaxy would be great to do more, and I'm hopeful that like with a combination of both the different like the orbital information as well as the chemistry, we might be able to tease out more about these very early the very early epoch of the Milky Way formation that is really, buried in the inner part of the galaxy because the galaxy was small at the time.
Okay, thanks. I think there's going to be an opportunity after the formal end of the colloquium to carry on these discussions. So before the end, I'd like to make announcements. If I just share the screen. Next week's colloquium, which actually is on also looking at the Milky Way's history, but from a different observational perspective, by Andrea Miglio from the University of Bologna, as always by Zoom, other things. Okay, so let's now just open our screens, open our videos, and give Anna a great send-off for this really wonderful colloquium. Thank you, Anna.